Alright, so let's look at this question. A liter of solution containing 0.1 mole of ethanoic acid and 0.1 mole of sodium ethanoate forms a buffer solution. So recall that a buffer solution is either can actually be a solution of weak acid and its salts, like this ethanoic acid and its salts here. It can also be a solution of weak base like ammonia and its salts like NH4Cl. So these are examples of buffer solution. So we are told to calculate the pH of this solution. Initially, the pH of the buffer solution was 4.74. So we are told to calculate the pH of this solution after we add a certain amount of a base, sodium hydroxide. So basically, this is the buffer solution. This is the buffer. Let's call this the buffer solution. So, and the pH of the buffer solution is 4.74. That's the pH. And this buffer solution is composed of CH3, COOH, and its salt, which is CH3, COONA. So this can be written in this form. So let's say this is the buffer solution, and the pH of this buffer solution is actually 4.74. So we are told to calculate the pH of this solution after we introduced the 0.2 moles of sodium hydroxide. So now we are introducing sodium hydroxide as 0.02 moles of sodium hydroxide. So definitely we expect the pH to increase because we are adding a base, right? So therefore, to calculate the pH of a buffer, we use pH equals to pKa plus log of salt over acid. So this is a simple way to calculate the pH of a buffer solution. So initially, the pH of the buffer solution was 4.74. That is, before we introduce the base, before we introduce sodium hydroxide, the pH was 4.74. But we're not given the Ka value and we are not given the pKa. So let's say pKa is unknown plus, and then we have log. So the salt was said to be 0.1 mole. So let's put the salt here, 0.1 and the acid also was 0.1, so we have it to be 0.1, right? So let's find out what the pKa would be. So this one cancels out to become 1. So therefore we have that the pKa equals to so we have it to be 4.74 minus 0, because log 1 is the same thing as 0. So we have the pKa to be 4.74, right? So the next thing we now have to do is to calculate the pH of the solution after we introduced this 0.02 moles of sodium hydroxide. So to now calculate the pH of the solution, we have pH to be equals to pKa plus log of salts over acid, right? So since we're adding an acid, let's write the equation to be this. So we have CH3 C00H plus the base that we are adding. So this is a neutralization reaction, and we should have a salt which is CH3 C00Na, right, plus H2O, right? So the initial concentration, let's call this initial. The initial concentration of this was 0.1. So the initial concentration of this was 0.02 moles, and then this was 0.1. So we neglect this actually. So the change in concentration, like the change, it was change. Let's put change here. This sodium hydroxide is going to completion, like we are using it to the end. We are pouring everything like 0.2 moles of it. So basically, this becomes 0.02, and this becomes negative 0.02, and this becomes positive 0.02. So this becomes the equilibrium change, therefore becomes we have 0.08 moles. This one goes off, goes to completion, and this becomes 0.120 moles. So now we need to like put this into the equation here. So we have the pH to be what? The pK initially was 4.74, and we have plus log of salt. So the salt was 0.120 over, so the acid was 0.08 molar. So the pH therefore becomes 4.74 plus 0.18, and that becomes 4.92. So this is the answer. So one thing you need to note about this is that I believe you got how everything was done. So but the most important aspect of this question is the aspect of the introduction of the base. So because we're adding the base, in fact you don't have to like go through this step in your exam or your test, because we're adding a base. It's increased the concentration of the salt. I want you to take note of this. The base contained Na, right, which is sodium. The salt also contained Na, right, which is contain Na. So basically, the introduction of this increased the concentration of this, and that's why this increased. Like this 0.1 became 0.120. What you can always do in your text or your exam is that when we introduce a kind of base like this, it increases the concentration of the salt. You just add this to this, and then you subtract this from the concentration of the acid. So you have 0.08, and then you'll be able to like do your answer, to get your final answer. Another thing you need to note is that if we are introducing an acid instead of a base here, assuming we are introducing, let's say we are introducing an acid like HCl, this we go in the other way around. Like we'll be subtracting from the salt and we'll be adding to the acid. I hope you got this. So now let's see the next question. Alright, so let's look at this question. A phosphate buffer consisting of H2PO4 and this, it helps to control the pH of the blood. So we are told to calculate the pH of a soft drink in which the buffer ingredient this and this. So recall that we said a buffer solution will always consist of a weak acid and its salts, or a weak base and its salt. So here's an example of a weak base. We have NH3 and its salt is like NH4Cl. And from previous question that we did, the weak acid is like ethanoic, and its salt is sodium ethanoate, which we have to be this and this. So in this question, it can actually be very difficult to like identify which one is the acid and which one is the salt. But just take note of this: anytime you see a charge like this, in most cases, that is always the salt. It's composed of charged substances. So we have this to be the acid, and we have this to be the salt. So now, to calculate the pH of a buffer solution, we simply use pH equals to pKa plus log of salts over acid, right? So from the question, we have our pKa to be the pKa was not given, but we have our pKa to be calculated from negative log of Ka, right? So our Ka is 6.2, which is A, 6.2 times 10 raised to power minus 8. So we have the pKa to be 7.21. Just press this to your calculator, you get the answer. So we have this. So now we need to calculate this aspect for us to be able to get the pH of this buffer solution. So for us to get this, we recall that we're given this in gram. So we need to convert this to mole per dm cube. So, and how do we do that? We have the acid to be NaH2PO4. So let's find the molar mass to be 23 plus 2 plus we have this to be 31, and we have this to be 64, which is no, we have it to be 64, 16 times 4. So everything here becomes 120 gram per mole, right? So also for Na2HPO4, so this is the acid and this is the salt. So we have this to be 23 times 2 plus 1 plus 31 plus 16 times 4, which is 64. So everything here is 142 gram per mole. So now the next thing we need to do is to convert this to mole, right? So we have this to become 6.59 gram of the acid, therefore becomes 6.5 over 120. Mole is the same thing as mass over molar mass. So therefore we have this to be 0.0542 moles. So also for this is definitely going to be we have it to be 8 gram. That will be mole equals to mass over molar mass, right? And that's 8 over 142, and we have 0.0563 moles, right? So now also we need to put this in 1000. The first one was 6.5 gram in 355 mils, and it's the same thing as, okay, let's write it out. Acid is the same thing as 0.0542 moles in 355 mil, right? So we need to convert it to mole per dm cube, and that will be 1000 mil. So this is x. So cross multiply, we have our x to be 0.153 mole per dm cube. So also for the base, for the salt, we have it to be the mole is 0.0563. That will be 0.0563 moles give is in 355 mils, right? So 1000 mil will give what? We give x. So cross multiply, we have our x to be 0.159. So now we need to put this value into this equation. We have our pKa to be the pKa was 7.21, and this the salt was 0.159, right? And the acid is 0.153. So when we do everything, we have our pH to be equals to 7.21 plus 0.02, and that gives 7.23. So the right answer is C, option C, 7.23. Alright, so let's look at this question. So we are told to calculate the pH of a buffer solution of methanoic acid and methyl ethanoate. So basically this is still a buffer system, right? So it's a solution of weak acid and its salt. So for us to calculate the pH, we are using pKa equals to log of salt over acid, right? So the next thing we need to do is to get the value of the pKa. So pKa equals to negative log of 1.48 times 10 raised to power minus 4. So we have this to be so this becomes 3.8 3, right? So this is the pKa. So now we need to calculate this aspect. So let's say that our pH equals to 3.83 plus log. So the salt is methyl which is 0.01 over this is the acid, which is 0.001, right? So let's multiply 1 2 1 2. So basically we have this to be 3.83 plus, so this becomes 1, and then we have the answer to be 4.83. So the answer is C, option C. All right, so let's look at this question. Which is all are correct about 1 liter buffer solution? So let's say the buffer solution is this. So we have let's say it's since the pH is 4.0, let's say it's weak acid and it's salt, right? So this is the solution and the pH is 4.0, right? So when you add 1 ml of an acid, the pH slightly reduced. Is this true? For us to understand this, let's see the pH scale. So the pH scale is this. We have 0 to 14, right? And here is 7, right? So acidity increases to the left hand side, like acidity like decreases in terms of the value of the scale, and alkalinity increases in terms of the value of the scale. So now looking at this question, when you add 1 ml of an acid, so let's say we added 1 molar HCl, 1 ml of it, so definitely you expect this solution to become more acidic. Assuming we added a base, then that could actually like increase the pH, but we are adding an acid, so you expect it to be more acidic, so it's slightly reduced. So this statement is actually right. So let's see the next one. When strong acid or base is added, the pH of the buffer is always constant. Is this true? We are not so sure. So if we are not so sure yet, let's look at it. We already said that option 1 is correct. So look at the options here. So this one does not have 1, so it should be out. B should be out. This one should be out. So this should be the correct answer. But let's find out. So when a strong acid or base is added, actually, the pH of the buffer is never always constant, actually. So the pH of the buffer is usually equal to the pKa of the acid component. This is wrong. So now let's see the last part of the question. We said the acid salt ratio of 5.0 will give a pKa of 3.0. So let's see this. They said, remember that to calculate the pH of a buffer, we have pKa plus log of salt over acid, right? But this ratio is actually acid over salt. So the pH will become pKa plus, this will become negative because we are changing this, we are inverting it. So this will be acid over salt. So now the pH was said to be 4.0 in the question. So we have 4.0 equals to, so the pKa, we are looking for the pKa, let's say it's x minus log of, so if this ratio is 5, then we have log 5 here. So basically log 5 is, so log 5 is 0.699, and this is x minus 1 equals to 4.0. So therefore we have it to be x equals to 4.699. So the pKa is not 3. So this is wrong. So definitely option D is the answer. All right, so let's look at this. What is the relationship between Ka and pKa? So the relationship is simply pKa equals to negative log Ka. So this is right, this is wrong, wrong, and wrong. All right, which acid is present in vinegar? The acid present in vinegar is acetic acid. Alright, so let's look at this question. Which of the following statements is or are not correct? So phenolphthalein is suitable for reaction of weak bases and strong acid. So basically, phenolphthalein works best in alkaline condition, like around 8.3 to 10.5, and it's like pink in color in this range. So phenolphthalein is colorless when it is like less than, when the pH is less than 8.3, it's colorless, right? So this statement that phenolphthalein is suitable for a reaction of weak base and with strong acid. So the reaction of weak base and a strong acid would give an acidic, like acidic solution most likely. So phenolphthalein is not suitable for determining the endpoints of an acidic solution. So this is wrong. So the degree of dissociation of an indicator does not depend on concentration. So this is also wrong. Degree of dissociation of an indicator actually depends on the concentration. So all indicators maintain the same color change over the entire pH scale. No, this is wrong. So the reaction of weak acid and base does not give a sharp endpoint. So this is the right one there. So which of the statements are wrong? So 1, 2, and 3 are wrong. So this is the right answer. 1, 2. Alright, so let's look at this. Which of the following statement is or are correct? So the pH of 0.001 molar H2SO4 and 0.001 HCl are the same. So this is actually wrong. The pH of H2SO4 is not the same as this because of the concentration of the because of the moles of the hydrogen ion there. When H2SO4 dissociates, it gives 2 hydrogen plus SO4 2 minus. So this is 2 moles. Therefore, we have it to be 2 times the concentration here. So we have it to be 0.001, and that's 0.002. So the pH of this solution is going to be negative log of 0.002, and this should give, so we have this to be 2.699. so this is the pH for this. But looking at the second one, HCl simply hydrogen plus Cl minus. So this is 1 mole, and that is the same as 0.001 molar. So basically we have the pH for this to be negative log of 1 times 10 raised to power minus 3, right? And so this is 3. So the pH of HCl and H2SO4 are not the same in the same concentration. So the pOH of sodium hydroxide is 3. Let's find out. So sodium hydroxide is basically this. We have it to be Na plus OH minus, right? So this is 1 mole, right? So and this 1 mole is the same thing as 1 times 10 raised to power minus 3, which is this one here. So the pOH rather, the pOH is going to be negative log of the OH there. So we have negative log of 1 times 10 raised to power minus 3. So we have it to be 3. So the answer here is 3. So this is right. This is correct. So the ionic product of water, Kw, is temperature dependent. Before we go to this, let's say this is complex that we can't solve it, right? So let's look at the options. We've said that option 1 is wrong, right? So the question says which of the following statements are correct? So anyone with 1 is definitely out of it. So this is out of it. So I'm also teaching you um how to like screen your options to be able to pick the right one. So, and we said that option 2 is right. So option 2 and 3 are right. So looking at this, let's go back to this. The ionic product of water is temperature dependent, and that is true. At 25 degrees Celsius, Kw is 10 raised to power minus 14. But as the temperature changes, this value changes. So it's temperature dependent. This is right. So you can find this out yourself. The Kb of this base is greater than 7, right? They said the pKb of this base is greater than 7. This is the answer. We have A. All right, so let's look at this question. So we have this reaction. Which of these statements is correct? So we have different definition of acid and base. We have Arrhenius definition. We have Bronsted-Lowry definition, and we have also the Lewis concept. So, but looking at the options here, we didn't talk about Arrhenius. So we won't talk about Arrhenius here. We only talk about Bronsted-Lowry and the Lewis concept. So Bronsted-Lowry defined an acid as proton donor, and a base as proton acceptor, right? So let's say we have the equation HCl plus H2O to give H30 plus Cl. So looking at this, an acid is a proton donor. Hydrogen chloride A lost its proton to H2O, and H2O became this. So what is left of this is chloride ion, right? This ion. So we can therefore say that this gave rise to this. This, after accepting a proton, became this. So this is an acid, and its product, what is left of it after the reaction, is a conjugate base. So also this is a base initially, so it accepted a proton. According to Bronsted-Lowry, is a base. So when it accepted a proton, what is left of this is this. So it becomes a conjugate acid, right? So also looking at the equation that we have here, they are quite similar. So okay, so looking at this equation here, we have that H2X react with 2BO BOH, which is boron hydroxide, to give B2X plus 2H2O, right? So this one react with this. It's lost its proton. This one, no, this is plus and this is negative, right? So it's basically 2 moles of this OH. But let's remove this. So this OH here accepted the proton here. It accepted the proton here to become this, right? And so this one also lost its proton to become this. So we have this to be this, and we also have this to be this. So this is acid, and this is its conjugate base, right? You can always use this part to identify whatever is left of this part here is the conjugate base. So here is Cl, we have the Cl, so this is the conjugate base. So also here is this, it's accepted the hydrogen from this acid here, and it became this. So this is the base, and this is the conjugate acid, right? So now the option says B2X is a conjugate acid. Is that true? Is a conjugate base. So this is wrong. So H2X is Bronsted-Lowry acid. So yeah, this is right. The Bronsted-Lowry acid. So H2X is amphoteric. For it to be amphoteric, it has to react with both base and acid. So let's say we are not sure yet. Let's put a question mark there. So let's look at what we've gotten already. So the question says which is correct. So basically 2 is correct. Anyone that does not have 2 is out already. So this is out, this is out, this should be right, and this is also out. So looking at it now, let's look at the last option. H2O is a conjugate acid. Yeah, we already said it, that H2O is a conjugate acid, and BOH is a conjugate what? Is it a conjugate base? No, BOH is a base itself. So these are wrong, these are wrong, and yeah. So the right, sorry, this is right. I mean, this H2O is correct, conjugate acid. So this is wrong. This also should be wrong. So the right answer is C. So this question says which of these compound is not an acid anhydride? So what is an acid anhydride? An acid anhydride is a non-metallic oxide that dissolves in water. When it dissolves, it gives what? It gives an acid. So looking at this, CO2, which is carbon dioxide, dissolves in water to give a weak acid. This also gives a weak acid. This gives a weak acid. This is water itself, so it does not give an acid when it dissolves in water. So the option D is wrong. So let's look at this. Which of the following is an acid salt? So this is a salt, but it's a normal salt because it is formed from strong acid and a strong base. So no, a strong base is sodium hydroxide, a strong acid is HCl. When they react, they form NaCl plus H2O, right? So this is a normal salt. So this is a sort of strong base and a weak acid, right? So since the base is stronger than the acid here, so this is a basic salt. So this is a basic salt. So looking at this, the most common way, like one obvious way to identify some acidic salts is that they contain some hydrogen, like in the middle of the equation like this. So we have this to be the acid salt actually. So this salt is also a sort of strong base and weak acid. So the right option is C. All right, so let's look at this question. So we're going to calculate the H30 plus concentration in a solution having a pH of this. So in this, the pH is calculated using negative log H30 plus. So we have the pH to be 5.73, right? But we do not have the log. We do not have the hydrogen ion concentration. So we simply have to take the antilog. So take antilog. We therefore have 10 raised to power minus 5.73. That's how to take the antilog. And then we should have 1.86 times 10 raised to power minus 6. So the right answer is C, option C. So let's look at this question. The degree of ionization of 0.01 molar acid, and the dissociation constant Ka equals to 10 raised to power minus 4. So we are told to calculate the degree of ionization. So what we need to do is this. We have Ka equals to C alpha square. So this is the degree of dissociation. We have the dissociation degree, which depends on concentration. We have this to be dissociation constant, and we have this to be concentration. So therefore we have that since the K is 10 raised to power minus 4, we have it to be 10 raised to power minus 4 equals to 0.01 alpha scale. So therefore we have it to be 10 raised to power minus 4 over 0.01, which is the same thing as 10 raised to power minus 4 over 10 raised to power minus 2. So we have alpha scale to be equals to 10 raised to power minus 4 plus 2, which is the same thing as 10 raised to power minus 2. So this gives us that alpha equals to root 10 raised to power minus 2, which is the same thing as 0.1. So the answer is B. So let's look at this question. The following are Arrhenius acid. So let's take Arrhenius definition of acid. Arrhenius defined an acid. An acid dissolves in water to give what? To give hydrogen ion or hydroxonium H3O plus ion. So basically, for it to produce hydrogen ion or this, there must be hydrogen ion in, like, there must be hydrogen in the equation. So one of the limitations of Arrhenius definition of acid is that it limits it to compound or substances containing hydrogen ion. So like HCl is an example of Arrhenius acid, because when it dissolves in water, it will give this H2O plus and the MCl minus. So it gives this. So that's the definition of Arrhenius acid. But looking at this, there's no way this will produce H3O plus or hydrogen ion in water. So therefore, this is not an Arrhenius acid. So this is an Arrhenius acid. So this is also not an Arrhenius acid. It's a base. So this is an acid. Yeah, this is right. And this is also right. So we have option 2, 4, and 5 as acid. So these are acid, but these are Arrhenius acid rather. So but these are not acid. They are not Arrhenius acid rather. So that's 1 and 3. So the right answer is A, 14. So let's look at this question. So the pH 0.1 molar solution of weak acid, HCN is a weak acid and has a Ka value of this. So which of the following statements is or are true? So the first statement is that the pH of the solution is 5.2. So remember that the pH, we calculate the pH of a strong acid using this formula. pH equals to negative log of K of hydrogen ion rather. So the pH of a weak acid, however, is calculated using pH equals to 1 over 2 pKa minus 1 over 2 log C, where C is the concentration of the weak acid. So take note of the difference. So therefore we have that the pH equals to 1 over 2. Remember that pKa equals to negative log of Ka. So we have this to be negative log of 4.9 times 10 raised to power minus 10. So we have this to be this is equals to 9.31. So we have this to be 9.31 minus 1 over 2 log C. The concentration of the weak acid is 0.1. So therefore we have that this becomes 4.655 minus this becomes negative 1 over 2. So we have 4.655 plus 0.5. So we have it to be 5.155, which is approximately 5.2. So this is a correct statement. So calculate the hydrogen ion concentration. To calculate hydrogen ion concentration, we use hydrogen ion concentration equals to roots Ka and C. So the Ka is what? That's 4.9 times 10 raised to power minus 10 times the concentration to be 0.1. So 0.1. So we have everything to be root 4.9 times 10 raised to power minus 11. So the answer is 7 times 10 raised to power minus 6 molar. So this is also right. So the acid is monoprotic, yeah, because it has only one replaceable hydrogen ion. So HCl is also monoprotic, H2SO4 is diprotic, and H3PO4 is triprotic, which is the same thing as polyprotic, whichever way you want to call it. So the acid is monoprotic. So which of the following statements are right? So 1, 2, 3 is right already. So the last option, the acid is fully ionized in solution. It is not fully ionized in solution. Only strong acids are fully ionized in solution. Weak acid are partially ionized in solution. So this is wrong. So the right option is B. So let's look at this question. Which of the following statements is or are correct? So the pH of 0.001 molar of ethanoic acid is this. So remember that this is a weak acid, right? So pH of 0.001 molar ethanoic acid is 7.74, and the pK was this. So let's confirm if the pH is 7.74. So this is a weak acid, right? And the formula for calculating the pH of a weak acid is 1 over 2 pKa minus 1 over 2 log C, right? So we have our pKa to be 4.74, right? Minus 1 over 2 log. So our C is what? 1 times 10 raised to power minus 3, right? So we have this to be 2.37 minus positive 3 over 2. So we have this to be 2.37 plus 1.5, and that's 3.87. So now the pH is 3.87. So this is wrong, saying that the pH is 7.74. So the pOH of KOH is this. So let's look at this. pH of a strong acid pH of a strong acid is negative log of H plus, right? So pOH of a strong base also is negative log of OH minus. So we therefore have that the pOH equals to negative log 0.001, and this is the same thing as 1 times 10 raised to power minus 3. So the pOH equals to 3. So this is right? So the ionic product of KW is temperature dependent. Yeah, it's temperature dependent. At 25 degrees Celsius, KW is the same thing as 1 times 10 raised to power minus 14. When the temperature changes, the value changes. So we've been able to say that 2 and 3 are right already. So option 2 and 3 are right. So the last one, we need to calculate this. So the KB of this is a weak base, right? This is a weak base. It's asking for the calculation of pKb. PKb is negative log of Kb, right? So the pKb of 0.01 molar ammonia solution is greater than 7. Let's confirm. So this becomes negative log of 1.8 times 10 raised to power minus 5. So this becomes 4.0 7 4 rather. So this is the answer. So this is also wrong. So the right options are 2 and 3. So option A is correct. So let's see this question again. Which of the following are Arrhenius acids except? So we say that Arrhenius defined acid as proton donor, right? And base as proton acceptor. This the so proton acceptor. So this is Arrhenius acid. So this is a salt, it's not Arrhenius acid. So this is Arrhenius acid. What you need to take note about Arrhenius acid is that they always have hydrogen, like H2, like HCl, H2SO4, H3PO4, and all of that. So this is not an Arrhenius acid, even though there's hydrogen there. This is not an Arrhenius acid. The hydrogen here is not replaceable, so it does not lose its hydrogen ion. So this is not an Arrhenius acid, and this also is not Arrhenius acid. So we have 1 and 3 to be the right answer. 1 and then 3 to be the right answer, and the wrong one. So the question says, which of the following are Arrhenius acid except? That's 2, 4, and 5. As 2, 4, and 5. Let's see the options. Yeah, 2, 4, and 5. We have 2, 4, and 5 here. But here is a gas. So Arrhenius acid has to be like aqueous. It has to be aqueous, not gas, because this gas would not lose its hydrogen ion. So the right option is A. So let's look at this question. So which of the following statements is all correct? So ACl3 is an Arrhenius acid. Remember that Arrhenius definition of acid is that an acid is a substance that produces hydrogen ion when dissolved in water. So this does not have hydrogen ion, so it's not an Arrhenius acid. So BH3 is a Lewis acid. So let's look at the concept of Lewis definition of acid and base. So according to Lewis, an acid is electron pair acceptor, and base is electron pair donor, right? So to understand what this means, let's look at ammonia. So ammonia is NH3, right? So and this is 7, so we have it to be 2 and 5. So we have this. So we have it to be 1, 2, 3, 4, 5, 6, 7, right? So the hydrogen, we have one hydrogen here, we have another hydrogen here, we have another hydrogen here. So this is a pair of electrons. This is a pair of electrons. It's not shared. So this, according to Lewis definition, this is a base. So and looking at this question here, Lewis acid, they said BH3. So BH3 is this. So this is 5, right? And that's 2, 3. So therefore we have this to be this and this. So we have 2 electrons here and 3, 1, 2, and 3, right? So the next thing is hydrogen. We have one hydrogen here, we have another hydrogen here, and we have another hydrogen here. So there is empty pair of electrons here. So this structure, this compound will accept a pair of electrons. This one will donate a pair of electrons. So this is a Lewis acid, right? So ethane gas is an Arrhenius base. So for it to be an Arrhenius base, it has to have at least, it must have hydroxide ion, because it will produce this when dissolved in water. So this is wrong. So aqueous of HCl is a Bronsted-Lowry acid. Remember that Bronsted-Lowry defined acid as proton donor. So this will donate its proton to the base. So we have option 2 and option 4 are correct. So B is right. So looking at this question, in a hypothetical neutralization reaction, which of the following statements are correct? I think we did this in the previous question. So we had HX plus BOH to give BX plus H2, right? So we can say it's the same thing as having HCl plus H2O to give Cl negative plus H30 plus. So here, what is left of the acid? This is the acid, right? And what is left of it is the conjugate base after it has lost its proton, right? So also for this is the base, right? And what it produces after gaining a proton is the conjugate base. So looking at this is the acid, and this is the base, right? So what is left of this acid should be the conjugate base. And looking at this X here is left over here. So this is the conjugate base, and this is the conjugate acid. So now BX is conjugate base. Is that true? BX is conjugate base, right? So HS is Bronsted-Lowry acid. So let's look at it. HS, yeah, it's acid. It donates a proton. It's a proton donor. So according to Bronsted-Lowry also, an acid is a proton donor. So BX is monoprotic. Yeah, BX is let's look at BX. BX is monoprotic. Okay, yeah. Let's put a question mark there first. So we have H2O is conjugate acid. Is H2O conjugate acid? Yeah, H2O is conjugate acid. Is BOX a conjugate base? No, this is not a conjugate base. It is a base itself. So we know that 1, 2, and then 4 are correct for now. 1, 2, and 4 are correct, and we are so sure that 5 is wrong. So here we have 5, here we have 5. They are wrong. So this one does not have this one that we're so sure of, 1 and 2. So it's wrong. So this is the right answer. So definitely this is a wrong statement. Alright, so this question, which of the following statement is or are not correct? So solution of aqueous ammonia and ammonium chloride can make a buffer solution. So this is right, because a buffer solution is a solution of weak acid. Let's say this is a weak acid, right? Ethanoic, and it's salt. This is its salt, CH3 CONA, right? So and a weak base is NH3. Its salt is NH4Cl. So this is a buffer solution. Also, this is a double salt, right? So the next thing is the pH of this solution is greater than 7. So this is an acidic solution. You can see hydrogen at the middle of it here. So this is an acidic solution. As like an acidic salt is formed from the reaction of a base with an acid that has more than one replaceable hydrogen ion. So this is an acid salt, and you expect an acid salt to be acidic in nature, and it should be less than 7. So the pH of this is greater than 7. No, it's wrong. So KOH will liberate this. So let's put a question mark here for now. So let's say 1 and 2 are correct. So which of the following statements are not correct? Which one is not? Which of them are not correct? So let's look at it here. We can see that we are so sure that 3 is wrong, and we are so sure that 1 and 2 are correct. So looking at the options here, So which one has 3? So this one has 3 is wrong. It's wrong. So we are so sure of this one. So anyone that does not have 1 is wrong. So this is right. So option D is the right answer. Look at this question. Which of the following statement is or are correct? Methyl orange is suitable for a reaction of strong acid and strong base. Or indicator. So the degree of ionization of an indicator does not depend on concentration. This one is wrong. All indicators maintain the same color over the entire PSK. This one is wrong. So the reaction of a strong acid and a weak base does not give an endpoint. Only the reaction of a weak acid and weak base will not give a sharp endpoint. So this was wrong. So which is correct? We have question option 1 to be correct. So D alone is correct. So let's look at this question. The pH of ammonia. So um the pH of ammonia, we are told to calculate the pH of ammonia given that the pKb is 4.74, right? So what you need to take note is that ammonia is a weak base, right? And we have different different formula for calculating the pH of a strong acid and base and pH of a weak acid and base. So for strong acid, we said we use pH to be equals to negative log of hydrogen ion concentration. pH of strong base, we said it to be pH equals to negative log of hydroxide ion concentration. So for weak acid, we said it's calculated using pH equals to 1 over 2 pKa minus 1 over 2 log C, where C is the concentration of the weak acid, and weak base will therefore be the pH of a weak base will be pKw minus the whole of this, so that will be 1 minus 2 pk, but it's not going to be A, it's going to be B, right? Minus 1 over 2 log C. So we therefore have that the pH to be equals to pKw, and pKw is always 14. That's the pKw of that's water. So we have it to be minus 1 over 2 pKb plus 1 over 2 log C. So therefore we have that the pH of the weak base here is going to be the pH will be, so pKw is 14, that one is constant. 14 minus 1 over 2. So let's quickly do the pKb. The pKb is negative log kb, and that's negative log of so we're already given the value to be 4.74 already, so that will be negative 4.74 plus 1 over 2 log, so C is 0.05, that will be 0.05. So therefore we have that 14 minus 2.37 plus negative 0.65. Yeah, so we therefore have that 14 minus 2.37 minus 0.65. So we have this to be 10.98. So this is the answer. Alright, so let's look at this question. Calculate the percentage dissociation of this weak acid. So HCN is a weak acid, right? So given that the Ka is this, so the formula for calculating percentage dissociation equals to amount dissociated over concentration of the acid times 100%. So the amount dissociated is the same thing as the hydrogen ion concentration. This is an acid we're talking about here. So it's hydrogen ion concentration. If it's a base, we are going to be talking about the amount dissociated in terms of the hydroxide ion concentration. So we have therefore that the percentage dissociation of this. So the concentration equals to 1.0 times 10 raised to power minus 2 molar, and the Ka equals to 4.9 times 10 raised to power minus 10. So we need to calculate the amount dissociated, which is hydrogen ion concentration. So hydrogen ion concentration is simply root of Ka times C. So we have this to be root of 4.9 times 10 raised to power minus 9 times, we have C to be what? To be 1.0 times 10 raised to power minus 2. So we have 4.9 times 10 raised to power minus 12. So we have hydrogen ion concentration to be 2.214 times 10 raised to power minus 6. So therefore percentage dissociation will therefore be 2.214 times 10 raised to power minus 6 over the concentration of the acid is 1.0 times 10 raised to power minus 2, or everything times 100, right? So we're going to have 0.0221%. So the right answer is option B. Is calculate the pH of a solution which contains 0.65 mole of ethanoic acid and 0.35 mole of sodium ethanoate in 1 dm cube. So what you need to note here is that this is a buffer solution, and a buffer solution is a solution of weak acid and its salts, or a weak base and its salt. So we are told to calculate the pH here. So the pH of a buffer solution is simply pKa plus log of salts over acid. So the salt here is the sodium ethanoate, and the acid here is the ethanoic acid. So let's calculate the Ka. We have the pK rather, so it's equals negative log of 1.8 times 10 raised to power minus 5. So we have 4.74, right? So the salt here, we have the salt to be 0.350 mole, and or mole, whichever one, mole per dm cube, and the acid to be 0.650. So therefore we have that log 0.350 over 0.650 equals to negative 0.269. So we have that pH equals to 4.74 minus 0.269 equals to 4.47, which is probably because of approximation should have been 4.48. So this is the answer. Alright, so this question says, which of the following acid is the strongest? So everything is given in terms of pK. What you need to take note is that large Ka value equals to small pK, right? And this equals to strong acid. So the Ka value is measured in terms of their dissociation in water. So when they have a large dissociation constant, Like when they have a large dissociation in water, they will definitely have a strong, they are definitely a strong acid or base. So let's say we have a large Kb dissociation constant for base, so it's going to have a small pKb, and that is the same thing as a strong base, right? So which of these pK is the smallest? So this is the smallest, right? The pK is the smallest. So this acid is the strongest. All right, so I want you to solve this question and drop your answer in the comment section. So if you are confused with any of the answer, you can also drop it in the comment section that you're confused with the question, and then I would respond to that. This is another question. A liter of solution containing this and this form a buffer. So we are told to calculate the pH of the solution after we've added this amount of sodium hydroxide. So this we've done it. So calculate this and drop your answer in the comment section. So solve this also and drop your answer in the comment section. I want you to try this. Yeah. So this as well. So kindly subscribe to this channel, please, if you have not subscribed. This will encourage us to do more videos, and do also share with your friends. Thank you.